Okay, we're now continuing to deal with matter, but specifically looking at solids. Later lectures will look at liquids and gases and so forth, right? What are the four? There are at least four phases, if you will, of matter. What are the four? I mentioned three just now. Good job. Anybody else who didn't hear him? Okay. Three stages we all know about, right? Or the three phases are solid, liquid, gas. So you take a solid, heat it up, it becomes a liquid. Heat it up further, it becomes a gas. What is the fourth state or phase of matter?
Plasma?
Yep, plasma, right? So plasma is where you heat it up so much that the electrons come away from the atoms. Or at least not all of them, but at least some of the outer electrons come out. So it becomes a charged gas. And a charged gas it behaves in ways that are different from an ordinary gas. Okay, in this lecture we're looking at, or this set of slides, we're looking at solids, looking at atomic bonding first. Atomic bonding is basically the linking together of atoms to form larger structures. So it's basically like we looked at the example of sodium chloride, where sodium positively charged, chlorine negatively charged. So this electrostatic attraction, right? The negative here attracts through conventional, normal electric attraction, electrostatic attraction, attracts the positive, which attracts the next negative, which attracts the next positive, and so on. So what happens is all the positively charged atoms kind of put themselves between the negatively charged atoms, because positively charged atoms repel each other, but a positive and a negative attract each other, and so on. So through a combination of such forces, you end up with every alternate atom being chlorine, to the alternate atoms being sodium. And you build this up large enough and you end up with a solid. When the bonding is strong enough, right, that it's not easily broken, you end up with a solid. If the bonding there is some bonding, but it's not that strong, you end up with a liquid. Much lower bonding, you end up with a gas. Or maybe no bonding between the atoms. Actually, no bonding between the atoms or the molecules, you end up with a gas. Mademoiselle?
How do they bond together? What holds them together?
What holds them together? Extra credit to you. Good question, right? Typically, I don't want to be inappropriate, but think of a relationship. What's it that bonds a man and a woman together? Very strange thing, right? Some kind of attraction, right? We use the word chemistry, we use the word attraction. We don't know what it is really in human terms. I mean, these are basically terms out of physics, if you will,
right.
applied to some strange thing that we don't completely understand, right? It's just that, like as a guy, I have a desire to be with a woman. I don't know exactly, I mean, apart from the fun aspects, I don't know exactly why, but it just is, if you will. Just like this, charges, in a later lecture we will see, yes, I think positive charges attract negative charges. We don't know exactly why. So that's an electrostatic force or electrostatic attraction. Just like we also talked about the fact that we don't understand why gravity works, and yet my mass is attracted to the mass of the earth, and we don't know why. So there is an attractive force that we call gravity or gravitational force that attracts it to my body. So we don't know why that works, but that just works. We call it gravity or gravitational attraction.
Okay, so there's
positive, negative charge.
There's no actual thing, like it's like gravity, or like it's not anything you can see or touch, or it's just
it's not something
force.
It's not something that you can see directly, but it's something that we can infer the presence of based on the behavior of something else.
Okay.
So it's kind of I mean, like going back to the relationship example, like if you look at a guy and a woman who are in love, there's no way for us to measure that. There's no way for us to do an experiment and say, okay, I've captured this love. Look at this beaker that's full of this blue liquid. That's the love.
Right.
No way. However, we infer the reality of that love, or the love between a mother and a child, right? We infer the presence of that love by the way the mom deals with the child. And I agree that a lot of the times you cannot tell that the child loves the mom based on the behavior, but some fraction of the time you can, right? Yes, sir?
And vice versa.
Oh, and vice versa.
You actually covered what I was going to say, but I think that'd be an ionic bond between a mom and a kid. Then you can tell one and not the other.
If you could, okay, if you could.
Yeah, just tossing that out there.
Okay.
Chemistry joke.
Good. That's good. So like one charge versus the other, right?
Right. The steels doesn't share a thing.
Mm-hmm. The what?
Ionic bonds, one atom, or
Yes.
one molecule
Absolutely.
rather, will steal electrons from another, whereas
Yes.
in a covalent bond they share. So, yeah.
Okay. Email me the joke, right?
It was just kind of rolling with the
No,
yeah. So it's like the nerdy.
no, I think it's something that's worth developing as a joke, right?
I'll type it up for you.
Thank you.
I guess I just don't understand. Like, I'm looking at that. It's very I mean, it's complex and it's specific.
Okay.
And I guess I just don't understand what tells the atom to do that and how to do it. And
Yes. So you see that this is a cube, right? Now, first, the complexity is just by adding additional cubes to this picture. So this picture can be broken up into a series of cubes like this. And these cubes, what happens is this atom is holding hands with that atom. So think of it like holding hands, right? Now, I'm not going to ask you to do this, but let's say the four of you here. If I were to say to each of you, okay, you have two hands, so I'll say, is that right? Yes, you have a spare hand. Okay, so I'm checking this. In 2 dimensions, this would work, right? So let's say that the two of you hold hands with one set of hands. Then you have an extra hand, so you'll have to turn around, and then you hold hands with him, the remaining hand with him, and with his remaining hands, he holds hands with her, and with her remaining hand, she holds hands with you, right? So you can think of these atoms, to a first approximation, as having 2 hands each, 2 arms and hands each. So if I'm an atom that has 2 hands, I can hold hands with 2 hands with one other atom, or 1 hand each with 2 other atoms. So we looked at water, right? Water was oxygen with 2 hydrogens. So oxygen can be viewed as having 2 hands.
right.
So it holds 1 hydrogen and another hydrogen. Hydrogen can be viewed as having 1 arm. So it just got 1 arm and that's it. Now other elements, so we saw an example of ammonia, NH3. In that case, ammonia is a rather strange creature that has 3 arms.
Okay.
So it can hold, right? So it can hold, let's say that I'm an ammonium, okay, I'm a nitrogen atom and you're a nitrogen atom. What happens is I have 3 arms, you have 3 arms. So we could hold all 3 arms and we're done. Or alternatively, we can hold 2 arms and you have a spare arm and I have a spare arm. And you can hold another hydrogen and I can hold another hydrogen. Or you can hold 1 hand with me, I hold 1 hand with him. So I've got 3 arms, I can hold hands with 3 different.
And those things can be holding hands with something else. And
Exactly, and that's how you end up building so much complexity in chemistry, right? So this is just one form of bonding, which is, as you'd mentioned, the electrostatic bonding, which is where ionic bonding, which is basically, it's like I have a positive charge, I have a net positive charge. Let's say you're neutral and I'm neutral. And what happens is, remember that we talked about the desperation of elements to become satisfied? So let's say I'm fluorine, and I have a strong desire to move towards, say fluorine is like number 9 over here. So what happens is fluorine is in this column, but it wants to move over here. So to move over here, I have to grab an electron from somewhere. So what happens is you happen to be the nearest atom, I just grab an electron from you. So I take your electron and I hold on to it. Now it's mine. So once the additional electron is mine, in terms of the shells, I feel full and satisfied. My hunger is gone. However, I have an extra electron. That electron says, I have an extra charge. I need a positive charge. So I may be satisfied as the, of course I'm anthropomorphizing a whole bunch, right? So I may be satisfied as the fluorine atom, but my electron that I'm holding on to says, I need a positive charge. And it turns out that you, from whom I stole the electron, you have a net positive charge. Because you were neutral, I took an electron, a negative charge from you, you're now positive charge. So what happens is, the negative charge in the electron that I'm holding then sticks out an electrostatic arm to you and says, hold on to me. So it's this extra electron in me that's holding on to the absence of an electron in you, because you have an extra proton, that now creates a bond between you and me. Right? So this is an ionic bonding. But then there's covalent bonding, where there's sharing of bonds, and then there's van der Waals bonding. There's a bunch of different kinds of bonding, right? But the most common are ionic bonding and covalent. Good question, extra credit. I love it when students speak up. Okay, so moving on, Okay, talking about X-rays now. Oh yeah, here are the crystals. Remember that we talked about crystals and how they're facets? A facet is just like a plane surface, right? So this table has a facet, a flat surface like this. It has another facet like this. It has another facet like this. So if you look at these crystals of whatever, okay, it says they're silver crystals. What happens is you can see there's a flat plane here, another flat plane here, another flat plane here, another, do you see? Flat surfaces. What happens is the silver is crystallizing. Let's say it's loose atoms that they're coming together to form this crystal. They arrange themselves in a regular periodic arrangement like the sodium chloride crystal, and as that arrangement gets larger and larger, finally it gets to the stage where you can see all of the face of one of these crystal arrangements, and you end up with a flat face, right? So that's what is going on here. Now, the regular arrangement of atoms in these crystals or in any material can be determined by something called X-ray diffraction. X-ray diffraction is where X-rays are basically electromagnetic radiation. They're like light, but they have much higher energy, very high frequency, higher energy. That's the reason why, you know, like if you go to the dentist and they take X-rays of your mouth, right? They put the film in, they shoot the X-rays, and the X-rays go right through your cheek, through the bone, right? And it's absorbed to differing extents, and then it makes an image on the negative, on the photographic negative. And the X-rays are able to do this because they're much higher energy than light. Light doesn't go through your cheek typically, right? So you create X-rays basically by having two electrodes. Like, first of all, there's a glass evacuated chamber with two metallic things, we can call them electrodes. Apply a high voltage, so you've got electrons that come from here and hit this material. This material may be copper or aluminum or something. The material, as the electrons hit the material gives out X-rays. So here are the green X-rays in this case. They're not green literally, but the rays are presented as green. You have a screen with a hole in it, so you block all of the X-rays except the X-ray coming here. Now here you place the crystal, whatever it is that you're trying to analyze. You place it here, and the X-ray beam goes to the crystal and then goes off in different directions, and you have a film that photographs the pattern that you get. This pattern is called an X-ray diffraction pattern. And this pattern can then be used to infer the regular arrangement of the atoms in the crystal. If we were to change the arrangement of the atoms in the crystal, these dots would move. Notice that this has a certain symmetry. It has a fourfold symmetry. Here's a center dot, here's a dot, 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 right? So fourfold means I can put a mirror plane here and it's reflected, mirror plane here and it's reflected across here. So if I rotate it through 90 degrees, I can, to a first approximation, I can get this. Kind of like we as human beings have bilateral symmetry, right? If you took a mirror plane, cut you down the middle, don't do this, but if you were to cut you down the middle, in principle you can reflect this half on the other, right? So we have a single twofold axis, if you will, twofold symmetry, whereas this crystal has fourfold symmetry. So based on things like this is what I did my master's on. Didn't particularly like it, switched to electron stuff, totally loved it. So nowadays I do this kind of stuff with materials, but I use electrons instead of X-rays. I didn't like X-rays, I loved electrons. Okay, introducing another concept dealing with solids is density. We all know what density is, right? It's the mass of a substance per unit volume. So you take the mass of the object, divide by the volume, that's its density. So here is an illustration where loaf of bread, pretty light, right? So you take the loaf of bread and you squish it as hard as you can to make a tiny little ball. Same mass. The mass is exactly the same, right? What happened to its density? Density increased because its volume decreased, right? So like the difference between a bagel, you can take a certain amount of dough and create a bagel or create bread with exactly the same dough, right? The difference would be yeast or not, or the amount of yeast and so forth. So the bread that is more poofed up is more dense or less dense? Less dense, right? Whereas the bagel, which is more like it's not as expanded out, is much more dense, right? So that's basically the concept of density. Now you can call this mass density, if you will, because it's the mass divided by the volume. the weight density would be the weight divided by the volume. So here's the mass. Now if you multiply the mass by gravity, that gives you the weight. So weight divided by volume will give you what's called the weight density. So if you're given the mass density, all you have to do is multiply by g, gravity, little g, 9.8 meters per second, to give you the weight density.
When like you were talking about like the bread that has more mass,
Mm-hmm.
or more volume but less mass, is it always just air that
Good question.
that?
I think in most of the examples that we would see in our day-to-day lives, it is air. But you could do the same thing in principle in a vacuum.
But it would have to be in a vacuum.
It could be in a vacuum, but then it won't be air, or you could use a different gas or something, or you could fill it with liquid,
Okay.
a light liquid, and you'd end up with similar results, right? Extra credit again. Yeah. So you may be maxed out. Are you maxed out? Should be? Okay. Then here's an extra.
You should roll over.
Here's an extra. But I do want you to speak up in the class. See, if I were to reward you so much that you don't ever need to speak up again, then I won't experience the joy and the pleasure of hearing you speak up
But
in
then
future
if you give me
classes.
5 points a week, I can speak up 5 times a week.
Oh. If we ever get to the stage where you're not able to speak up, let me know, and you'll, right? I mean, seriously, for me, it really is fun to teach when students speak up, ask questions, right? And I try to set up an environment where you're not dissed in any way, right? Which I think I'm reasonably good at doing, right? If anybody, seriously, do I ever? No. you had me all worried there for a moment. Yes. Okay, next concept dealing with solids. Elasticity. We all know what elasticity is, right? So think of your socks, or the waistband of your underwear or whatever, right? And you know what happens if you wash your clothing too many times and put it to the dryer? What happens if, like, up to that point when it's new, you pull it and you let go and it comes back to its original shape? But then after you put it through the dryer too many times, what happens is you pull it and you let go and it stays pulled, right? What has happened is the material has lost its elasticity. So elasticity is the property of the material where it changes shape when a force acts on it, then comes back to the original shape when the force is removed. So here's an illustration. A baseball bat is used to hit a baseball, and you can tell that there's an indent now in the baseball, right? As the bat is hitting the ball, there's an indent in the ball. Now, the ball hits the base, or the bat comes and hits the ball, creates the indent, then the ball springs away from the bat. When it springs away, what happens is indent fills out again. It's just like, I mean, if you can, you've probably all done this experiment, right? You take your finger and you poke it against your forearm, and what happens is a depression now in your forearm. If you don't poke it too hard, you let go, the depression fills out. If you poke it really hard, your finger goes through, and then you've got problems, right?
You retain a lot of water and it just stays.
Oh, yes, good point, right?
I've been pregnant before, so I know that.
Oh, so like, okay, so like what happens is like all over this water retention, and then you press and it stays.
It just like stays. It's weird.
Really? How long does it take for?
It stays indented.
It stays indented?
For, I don't know, 10 minutes or something.
I had never ever. I just see. This is a reason for me to teach. Nobody has ever told me.
Oh, it's slippery.
I'll have to look when I get pregnant. I'll have to make sure that I.
Check your ankle. Or you can just go hang out at an OB's office in the waiting room.
Oh, and then ask all these women, can I?
Poke your ankle? Yeah.
Okay. Oh, is it the ankle typically that? Okay, cool. I don't know why. I have no idea. Something to do with the hormonal change. I don't know if there's a benefit to water retention when you're pregnant.
No.
There isn't?
Bad. It usually means you have hyper.
Oh,
or
okay. Yeah, your blood pressure is too high? Is it? Okay. So it's like a symptom. Cool. Well, I just learned something. Thank you. Extra credit for teaching me. Okay, I confess that I have never been pregnant, for whatever it's worth. Right? You can eat a lot of salt, and that'll, like a diuretic.
Eat a lot of salt, and then you could probably try it on yourself, and it might work.
Oh, I see. If I want to get the feeling of how it feels to be pregnant, then I eat a lot of salt.
Well, not to be pregnant, but to.
Oh, I see.
Like this.
Okay. Thank you. Extra credit to you. Are you maxed out too? Good. Okay, Hooke's law. I want the people who speak up to be maxed out. I'm a capitalist. I believe in rewarding people for for working, for thinking, for doing stuff, right? Okay, Hooke's law. Now, this is elasticity, and it's along the lines of elasticity. Basically says that the amount of stretch or compression of an elastic material is proportional to the applied force. So here, my pointer, if I apply a very low force, it bends a little bit. If I apply a larger force, it bends even more, right? When I let go, it springs back. So this is saying that the deformation, the delta x is the deflection, if you will, or the stretch or the compression, is proportional to the force applied. Now you can take this and make it an equal sign by applying a constant. So force is equal to a constant multiplied by the deformation, right? The extent of the deflection. K is the spring constant. So here is an illustration where we have a spring and we apply a small weight, we have a little bit of deflection, increase the weight, the deflection increases, right? You can see the spring is getting stretched more and more and more as you increase the weight, right? This is a direct consequence of Hooke's law, that the harder you pull on the material, the more it stretches. Application of this to this kind of a structure is called a cantilever, where you have a plank of wood, for instance, it's attached to a wall at one end and not at the other end. You put a weight on this end of the plank and the entire plank bends downwards, and what happens is the dashed line in the center does not experience any compression or tension, whereas the top becomes larger. It experiences a force that pulls it apart. So when I bend this like this, the top is experiencing a force that's pulling it apart. The bottom is experiencing a compression. So top is in tension, bottom is in compression, right? So compression means you're being squished. Tension means you're being pulled apart, right? And right in the middle, which is in between the tension and the compression, is the neutral axis, where there's no compression or tension. So the length of this blue line is the same before and after you place that weight on top. Now you've probably seen this experience, like if you go to the zoo and you happen to see a park bench, and it turns out that one of the elephants comes and decides that it's tired and sits on the park bench, right? You've probably all seen this. The elephant sits on the bench, and what happens to the, right? It sags in the middle. What is happening in this case is the weight of the elephant is pushing down on this, causing the bench to sag. Now, the bottom here, away from where the push is in tension. And the top of the bench is in compression. And again, the blue dashed line is the neutral line, neutral plane, neutral axis, where there's neither tension nor compression. So, in a case like this, supposing this plank we're going to crack open and break, would it crack open at the bottom or the top of this plank? At the top. In this case, would it crack open at the bottom or the top? Bottom, right? So there's a whole field of failure analysis for those of you who are in the airplane, aerospace kind of industries. There's a whole field of analyzing when something goes wrong with a plane, right? What kind of, like a crack in a wing, that kind of stuff, like where did it originate? Was it under tension, compression, all that kind of stuff? And then you redesign your wings and your planes and so on to try to minimize the odds of that happening. Now, we said that the neutral plane is about the center. So if we had, so think of this like a metal beam, right? You're building a skyscraper, really tall building, and what happens is you need to have these metal girders to provide strength to the building. And the metal girders can go up the walls, they can go, typically it's like reinforced concrete or something, but you could have, actually there are many buildings that are built with metal frames, right? So vertical metal frame, girder, then a girder going across here, and then you rest the floor on the girders, right? So that's weight bearing. So these girders, in this case, notice that this is shaped like an eye, so you could call it an I-beam. They remove the central, all of this material here, because the material here is under, when you place the girder like this and it's being pushed upon by the weight and it's trying to bend like this, we said that the top of the girder is under tension. Nope, it's under compression, and the bottom is under tension, and in between the stress is lower, right? The neutral plane is 0. So what happens is you can remove all this material, it's not needed, and leave the material here and here to withstand the maximum tension and compression, right? Now the benefit, what's the benefit to doing this instead of just having a solid beam? Less weight. So less weight, less material, right? So it's cheaper, less cost of iron or whatever, plus it's extra credit to whoever spoke up, and it's lower weight, which means that your building is not as heavy, probably means that for the same weight you can build a much taller building, and all that kind of stuff.